So great, we're live on YouTube and we'll start in just a minute. Great, we're live on YouTube. We'll start in just a minute. Great. So welcome back, everyone. So to the last lecture of spring 2020 for the data mining course. So thanks for bearing with us as we've so transitioned to be fully online. I think hopefully I think most of the course content has translated online so far. So hopefully your learning experience has still been acceptable. If you're coming to some stuff late, all the material is still online, so you can catch up once things are hopefully not as crazy anymore. The last thing we'll have to figure out will be the poster session. So the lecture today is going to be on finding and understanding these community structures and graphs. But before we do this, let's look at the schedule just for a little bit. So as you can see, we've completed everything, basically everything we had planned to complete for the semester. And there's a few small things that got dropped, but I think we covered pretty much everything. The end term test is going to be on Monday. Material about that's been discussed and posted online. I will post the actual end term test Sunday night by 9 p.m. and you'll have until Tuesday morning at I think like 2 a.m. to turn it back in. You should take it over and at most an 80-minute period. It should be like the midterm test, just material will be the second half of the semester instead. So you kind of should, most of you will finish in far less than 80 minutes, I expect. Then there's a homework due next week, Wednesday. I expect this not to be too challenging of a homework. The final reports are due today. So if you haven't seen, I pushed back the deadline on Canvas until midnight. If you have other kind of extreme circumstances, feel free to contact me as well about that. I think it's best to try and keep the deadline as close to where it should be. Otherwise, everything just gets pushed back and you get in more trouble later. But let's, I think turning in by the end of the day today should be fine. So the next thing on the schedule we haven't talked too much about yet is we're going to create posters for the projects too. There's a poster outline, which is going to be due next week, Monday. All right, and then we'll have a poster session during the space of the final for the class. Should be on a week from Friday, and I'll post more information about how the actual poster session is going to actually happen. I've got a plan that I am hopeful is going to work pretty well. And, part of the whole idea of creating a poster and the poster session is, I think it's important to learn to actually present and discuss and field questions about your work and to see what other people are working on. I think it's a pretty important thing to do. And so we're going to combine that with what's becoming another important skill is having these like online meetings. And so kind of part of the poster session is going to bring that in together, right? So I think this will be a useful thing to do. It should be a fun thing to do. Maybe not quite as fun as if it was in person, where you get kind of 150 people in the hallway all together excited about their work. But that's probably not a good idea to do either. So I think an online thing is going to be is going to hopefully be a good replacement for that. So before we start about this, let me just talk about the posters. So I want you to turn in a PDF of a poster in Canvas, right? And so this is a deadline next week, Monday. And it's that's not when the actual posters are actually due, but the point of it is, just doing it is one thing, but getting actual feedback on the poster is something I think also helpful. Please turn it in by Monday, and we can kind of give you feedback. It won't be finalized until we actually sign off on the poster. I have a certain standards for what I think a poster should look like. And even though I'll try and give you instructions, including some now and some kind of will be posted online about this, this is not, right, I think not all of you will get it quite right on the first try. And I think just a little bit of feedback can be very helpful towards making the posters even nicer. So let me kind of think about when you're thinking about a poster, typically in the past, we've printed them so that it was 3 feet this way by 2 feet in this direction. There's a template I just posted on Canvas. This was in the chat from last lecture as well, but I posted on Canvas now. That is for undergraduate research. They have a template for a poster. This has been actually the same template has been floating around, and a bunch of people have used it in the past few semesters. It's in PowerPoint. PowerPoint's actually turned into a pretty good tool to make posters on. I do them usually inside of Omnigraphal, which is a Mac program instead. You can use whatever program you want. One important thing to think about is you want to keep it in vector graphics. So don't save it as a JPEG or a PNG or like a bitmap. That stores every pixel and it reduces the resolution. A vector graphic stores the letter and by kind of curves and describes them with like polynomials. If you draw a box or an arrow, it describes the exact box, not just the pixels which are viewed of it. So a PDF or EPS, those things are vector graphics, and that's what we would prefer. Okay, when you're thinking about a poster, the most important thing is to have a title at the top. Okay, this should be the same as on your project report. Okay, the title should typically not be too long. It should be easy to read and catch someone's attention about what the what's going on in there. We'll have some sort of, for the poster session, what we'll do is we'll organize. We're not sure if this is going to be a spreadsheet or just a web page with links to all of your projects on them, and they're going to have the titles. And people are going to go and look at your posters and interact them and ask you questions. We'll probably, the plan is to have all the posters with links online, and then having each of you set up a Zoom room where you can host questions, and every person will have a first fixed amount of time where they'll be available, which will be posted, and other people can go during the window of the final exam and go and interact with the posters. And you want to catch people's attention with your title. My personal experience here, I'm going to have to go visit all 53 posters, and that's going to be hard to do within the 2-hour window. So you want to try and make this catchy. Right. So, so someone posted, you gives free access to Adobe Illustrator. Right. So this is a really powerful tool. I'm not sure if this is for everyone or just for students, but it's a really powerful tool. And if you figure out where you can download the software through the US using your student ID, you can get this. This is a great tool for doing this. Yeah. So this is like another good thing to think about. One thing to keep in mind, you want to have lots of these kind of a chart, where you have two lines you're comparing, or a figure. You want to have these in your poster. These are so like these very kind of important things to have in a poster. If it's just text, no one's going to want to read all the text probably. Okay, so you don't really have full sentences. I typically, and this is common, I've talked to people who are professional poster designers. This is a thing. Kind of having 3 columns works pretty well. The rule of 3s is pretty important here. And you typically want to think of the reading through it kind of goes in this order, where you start here 2 and 3, okay, and kind of run down these columns. But whatever is going on in the very middle here is kind of the most important thing. Okay, so you want to have usually a big kind of graphic or chart or something that you want to draw people's attention to in the very middle of the picture. Usually the top of the second column is a great place to do that. And so the way I like to do it is to have like an intro here, kind of a problem kind of setup here. Maybe this is talking about your data, right? And kind of there's some motivation going on in this column. And then in kind of the second column, you have like, boom, this is something cool, exciting that's happened. And then you kind of explain, then you're kind of explaining what's going on. Sometimes you have more charts and figures in the third column, and 2 is setting up some interesting kind of challenge, and then you answer it in the third column. Sometimes you have a big result in the second column, and then you have details on how you got it in the bottom of the second and third column. You can have kind of thanks and kind of explanations down here in the bottom. But, in the class poster, this isn't strictly necessary. And again, don't have long text, like no more than 1 sentence per section is one way to think about it. Use bullets. You don't need full sentences. I don't want to read a book while I'm looking at your poster. I'm going to be coming by your posters, and I'm going to be spending 2 to 3 minutes per poster. So I'm not going to be reading a lot. I'm going to look at the big pictures, and during that time, I need to be interacting and asking about it. So I don't have 2 to 3 minutes to read it. I'm going to read your poster in like 30 seconds. Okay, so you better make these big things that are easy to catch someone's eye, and then have details in certain places where you can answer follow-up questions. Oh, to do this, there's this one thing on the poster that I want to point to, right? So a great way I like to think about this is if you were to explain to me what your work was about and had stuff you wanted to point to me to explain what it was about, or someone else in the class, those are exactly the things that need to go on your poster. The stuff that you would not really use in explanation does not need to go on a poster. I'll have your report. You can bring your report and attach it to if you want to explain stuff. But the visual aids and the kind of the outline and the structure you want to use to explain it, that's what goes on the poster. All right, so any kind of major questions about this? In the past, we brought back in the posters from the previous iterations of the class I had at the start of the semester. These are previous students' work, and I've kind of gotten permission to share them in a closed environment, but I don't want to post them publicly for examples, but hope you remember back what some of those examples were like. They kind of do something fun, do something catchy. You don't need to use this template. People have done things like a template that looked like a newspaper or kind of something that had to do with the theme of their project, and doing that was more fun. Something that's going to happen is you're going to be able to vote for your favorite poster, and the posters that get the most votes are going to get some extra credit points. And the best posters are usually pretty cool, right? They either have really cool results, the topics are cool, they have kind of cool organizations of what's going on, they've done some cool stuff, and so kind of, you know, try and do this. It's a fun experience, and I think a very useful experience. All right, so let's move on to the topic of the lecture today. And so I'll talk about communities and graphs. So communities in these graphs, and this will mainly be talking about some like these graphs that have arisen from like social networks. And you know, if we finish early, I'll open it up to questions, and you can ask me other things, maybe some stuff about MapReduce that we didn't cover. All right, so again, we're thinking about kind of a graph, and this is usually written as G, which is a vertex set and some edges, right? And now we're going to think of these vertices, and particularly in this lecture, these vertices, these are, think of these as people or entities. So to think of this like like a social network like Facebook or Twitter, and there's typically some relation, like this person. So if they like follow someone else, then you put an edge, and this can be a directed edge. And for most of this stuff, the direction does not matter too much. In the web graph, when we were talking about PageRank, there the direction was actually pretty important, because we're looking at kind of the flow of information of like this random surfer through the graph. I've seen studies that have tried to say, okay, let's try and figure out how to, you know, most of these things are done without looking at the direction too much. And so I've seen studies that said, let's try and add the direction back in and look at the change and how the analysis happens. And it's usually pretty small. And there have been people said, okay, what's the best approximation I can get by adding weights but removing direction that I can get, and the techniques, what do they look like if I try and apply techniques that don't have the direction using directional information? And usually the best approximation is just remove the direction, so it becomes bidirectional. Okay, it can be follows, or it can be there's a friend in between these two people. Okay, so how you define edges, right? So these define the edge. So how the edges are defined is like a modeling choice. Okay, so there are lots of ways to define edges between people. So one is that they actually there's actually a friend, or they follow someone on Twitter, but there could be other thing where they actually reply to their tweets, or they actually interact with the friend in some way by kind of posting something on their message on their page, right? And so there are richer ways you can model these edges. It doesn't just have to be just follows or just the friend request. And this is kind of like corresponds with like the notion of distance when we're dealing with things like clustering and dimensional reduction, where if I change the notion of what an edge means, it completely changes the structure of the graph and completely changes the end of what sort of communities I end up following. These tend to be more kind of hierarchical, that, you know, I can't send a message, I can't see someone's tweet or reply to if I don't follow them on Twitter, for instance. So it's kind of, It's not quite as important, but it's still this modeling choice feature of how the edges are defined. All right. Okay, so now we have all these edges in this graph, and what we would like to do is to kind of find this kind of structure where there's this tight relationship, that there's a lot of edges in between these nodes on the graph, where I don't necessarily want to kind of include something like this, right? These two might not be in the same group. They aren't connected to each other, and none of their friends are connected to each other either, right? So they should be in the same one, but the green one, this would be a subcommunity in the graph in some way. There's a lot of edges in between these vertices here. All right, so right, so this has been like this was an area of research that has existed for a long time, actually, but really kind of came to a head about like 10 or 20 years ago, where 10 or 15 years ago, we really started to understand what was going on in this. So there are these old studies, these like, well, so first I want to say that, like a lot of these early web businesses, so think like the .com boom, right? So this was around when things like Facebook and like MySpace were just getting off the ground. They were trying to create these social networks like GeoCities, and a lot of these websites, their ulterior motive to doing what they're doing, they're trying to sell some product and maybe deliver ads, but they, if in a lot of the VC pitches, if you believe that those were a good indication of what was actually kind of the good, real innovation back then, but in the late 90s, a lot of the venture capitalist pitches were actually going to create this online environment, and it'll allow us to understand human dynamics in a way we haven't understood before, and we're going to then be able to maybe more, this more focused community opens up all sorts of stuff. Right, and this was true way before these social networks were actually successfully created. I was friends with someone who kind of worked at the university where I was kind of in this lab. His side gig was the CTO of one of these startups. He had done a PhD at Stanford and just finished and become CTO of a company along the way. And he said they were basically selling ads and giving lots of VC money, and they pitched it entirely based on getting on their trying to create this like social network, not that they were actually trying to sell ads in this other way. The company eventually failed, but it was one of these that had millions and millions of dollars of VC funding. So like this has been studied by like the field of like sociology for, at least like 50 years, right? So and they were trying to understand these notions of like social networks. But so in order to do it, they actually tried to collect data, and there were a bunch of these instances. Like there's this Zachary Karate Club data set, which was a pretty good example of what these things were like. And they would actually, they would actually manually collect, and this means someone, a sociologist, a grad student would go out and try and kind of interview people to try and figure out who's connected to doings in some like network, right? So you can think of that the V was on the order, the size of the nodes was on the order of, say, 100 to 200. This would be like a large data set, okay? So in the range of 100 to 200 would be a large data set. So think of these kind of nodes. And so example of this would be like people in kind of, or let's say, so seniors in so high school, okay, and then you would say that there was an edge if these people were so let's say friends. Okay, there could be other relationships which are matched. And I think in my high school and college, we actually made one of these big charts at some point, and it was collected and maintained entirely by hand, by rumors, by other stuff. You just try to collect who's friends with who in the high school. Okay, and so, you know, when you only have 100 or so nodes, certain things look different. You'll notice that pretty much all the graphs I'm going to be drawing in this lecture are going to be ones where I can basically draw them on the page. These graphs are planar, right? So a planar graph is one where basically you can draw it on a sphere, and by very stretching out it, as you can, if you can draw it on the surface of a sphere, there's ways to stretch it out so you can draw it on a plane, basically so that no edges cross and you have straight line edges. Okay, and so this allows you to kind of see what's going on pretty easily. And there's research in kind of how do you draw the best way with straight line edges and so forth. And maybe you have some edges which cross here. Actually, this graph is still planar, even though this edge crossed. There's a way to move kind of, I could move these two vertices over, kind of invert them, move them over here, and it wouldn't cross. Okay, but if I draw enough of these edges, let's say I also draw this edge here, then there might not be any way I can draw it. Okay, so I might have some edges that might need to cross, but I don't have too many. And I can get a pretty good understanding what's going on just by looking at it. I think I have a good understanding. Yeah, but this kind of hits some kind of structure. It looks like if you see clusters, then you can just kind of like circle the clusters. You know, like I said with clustering, if you could draw it in 2D, then just try and circle the clusters, and this is a pretty good approach to doing it. That was probably a reasonable thing to do with this size of graphs as well. What happens when you draw it, when you have, let's say, when the number of nodes becomes, let's say, greater than 1,000 in most graphs, is what happens is you get these structures where you get a bunch of, you know, the best drawing you can do ends up looking like this, where I have this dense collection here, and I have all these edges kind of in here that's all clustered up. I have a few edges kind of coming out of this, and I also have a few nodes which are not connected to anything here. So this is a pretty typical structure. This is called a this graph would be called like a hairball graph. This is actually what it's called. There's a way to quantify it being like a hairball graph as well. And there's really not a good way to do it because there's usually this tight part in the middle here that has tons and tons of edges, and I can't draw them in a way which is planar anymore. So when things get big, I end up not being able to draw them and to see what's going on. Are there multiple kind of groups and communities inside that hairball, or are there not? You know, how can I tell what's going And so this is a big challenge, and we need to use more automated ways to do this. There's actually some various studies. So people said, okay, I can't collect large graphs, but I can develop these mathematical models of these large graphs, and then I can study the mathematics of them. I can say, will there be clusters or not of a certain type? And so the most famous of these was called the Erdős-Rényi model of the graph. And basically, there are two basic variants of this, but they basically say, I pick n, which is this size of the nodes, and then I choose p, which is a probability between 0 and 1, and then I say every edge exists independently with probability p. Okay, so every edge, I look at every potential pair of vertices, and I say that edge exists or does not exist with the probability p. And so this was, and what this model was very nice in that I could study what happened. Let's say I pick a large enough n, and then I look what happens as I increase p, and you see, okay, yes, at a large enough p, I get this hairball structure. And then a large enough p, basically everything is connected to each other and pretty tightly connected when p is equal to roughly, they're roughly, if they're roughly n log n edges on the graph, then I get this very tight hairball structure, and right around then it becomes either from disconnected to fully connected. And the transition is these leftover nodes which aren't connected to anything until once they're connected, then everything is connected, and cycles start appearing at a certain rate, and you can study this mathematically. Okay, so it turns out, as we'll discuss, this model is not actually the way any real large-scale graphs actually look. But up until the 1990s, this was model everyone studied for large graphs, basically. And it was basically wrong. Okay, so we realized once in the 90s, these internet companies came along, started creating successful social networks, and then they could study what was going on. They said, look, the sociology implications and kind of theories, which are based on drawings about 100 nodes or so, weren't necessarily correct, or that there were debates of these things. I'll mention one shortly. And this Erdős-Rényi model of large random graphs also didn't quite capture what was going on. They were missing certain features of these things. All right, so let's start now with a question. So let me try and make a concrete question that was studied in sociology, and there were multiple theories of it, and they didn't know which was correct. There were theories in that people wrote papers and said, this is why I believe this is correct, right? Okay, but they didn't have enough data to test any of these theories. Okay, so let's start with some graph, okay, inside of here. There's some graph, and then there are some edges in this graph. Let me see if I can draw a good example. Okay, so there's some edges in this graph. And then I have two people. I have Xavier and Yolanda. Okay, and each of these, and so this graph itself is, let's say, this graph is some form of community. So these are these are all people who go to like yoga together. They're all in a yoga class, or they all belong to the same church. There's some sort of known community here. And then I have two people who have independently are not in the community, but they have 3 of these. Okay, let me add one of these edges here. Okay, so there now each of these people have 3 edges into this community. Okay, but they're a little bit different. Okay, so with Xavier, all friends are so connected. Okay, and with Yolanda, no friends are so connected. Okay, so if you notice, Xavier's 3 friends within this community all have edges in between each other, but with Yolanda, the 3 friends in the community don't know each other, even though they're all inside the same community. It's a big yoga group, but they sit separately, or a big church. They don't sit together inside the church, but they all happen to go, right? Whereas with Xavier, he's got 3 friends that are going to the church, and they're all friends inside the church. They sit together, and then they go out for lunch afterwards. Okay, so who is more likely? Who is more likely to join this community? So is Xavier acts more likely to start doing yoga or to go to the church, or is like Yolanda more likely to do this? Right. So and there are views on both sides, and kind of think to yourself right now if you want to there's a view for try and make up your mind. For Xavier, the idea is if he joins, it's because there's this strong support. They all 3 of his friends can get together and jointly to get him to join, and he'll join, and it'll be part of a really strong sub-community within this kind of subgroup within this community. So it'll be fun. Whereas with like Yolanda, the theory was she's more likely to join because she has this independent support. 3 people who don't necessarily know each other are all telling her to join this group. They're not just saying it because they happen to be friends and wanted to join, but they're independently saying that they want to join. Okay, so let's try this raise your hand function. I'm not, so we'll see if this works. Raise your hand if you think Xavier is more likely to join. I see 2 people have raised their hand if they think Xavier is more likely to join, and who thinks Yolanda is more likely to join? All right, so 4 for Yolanda. So let's see, Xavier got 2 votes, Yolanda got 4 votes, and about the rest of you decided not to vote, which is fine. So it turns out that now that we have these social networks and we can see how they're forming, we can have these communities like a Facebook group that people jointly chat about something, and we can see, okay, if they have these statistics, who is more likely to join? And it turns out the answer is going to be Xavier. Xavier is more likely to join. So it turns out these tightly connected kind of subgroups are a really important important feature. These tightly connected groups tend to form, and these and they're more attractive towards these things than these independent supports. This is something that's been observed experimentally. Now that we can collect lots and enough data to actually have, there was this debate for, I don't know if it was decades, and then it was basically settled by actually collecting data on this. There's this not exactly the same thing, but there's this important theory about graphs that changed it, which was not true in these like in like these Erdős-Rényi models, where you would not have ever seen this, very rarely seen this structure, this tight communities forming in these Erdős-Rényi models, because it would have to be that it's a low probability event. You would see all of these things happen together. But in real graphs, this would happen all the time. And so this is captured by this main idea called preferential attachment. Okay, and so basically, if A is connected to B and C is connected to B, and if there's D over here, then I'm basically more likely to form edge AC than AD, right? So I'm more likely, this would be like essentially some random edge from A to D would be like a random edge being formed under these old models, where AC is saying, well, if there exists some connections, I'm like, I can get there with one hop away, then I'm more likely to form this edge, right? If I'm already friends with B, you know, if I'm Adam A and I'm friends with Bob, and Bob is friends with Claire, then I'm more likely to be friends with Claire. Maybe Bob introduces me to Claire, right? And this totally makes sense. Probably, you know, if you think of the previous thing, if I am in the same group, I'm more likely, if I'm already in the same community, I'm more likely to form edges in there. There's some locality in these graphs. Even though they're all online, there's some net sense of locality, and this is sort of capturing what's going on. Right, and so there have been these newer models, and there are a variety of them, of what large random graphs try and look like, and they've kind of looked at what are these densifying features based on this preferential attachment, and they figure out how to generate large random graphs that sort of have these properties. And you can do things like, and there are other things where like there are certain nodes, they're also going to be with the random models that are independent, all the nodes are going to have roughly the same degree. There could be some that are bigger, but it's going to be kind of follow like a central limit theorem where it's more concentrated. Whereas in real graphs, certain followers have many, many edges. You'll get these star formations where I'm going to have a certain node that has lots and lots of edges coming out of it, right? So, you know, an average person on Twitter, average kind of person on, say, Twitter is maybe followed by, say, roughly, you know, let's say something like 500 people, right? There are some more, some less. You know, I'm not too active, so I have probably under 100 people following me on Twitter. But then the most popular person, so this is, I think Obama is still the most popular. He has something like 130, so like million followers. Okay, so this is like, and several orders of magnitude larger, right? There are so many people who follow Obama than an average person on Twitter, where you can think about the number of edges in the graph. The number of edges in the graph is probably something, if it's like average 500 people are followed, then it's the number of people on Twitter times half of that number, right? Times, or maybe it's still times 500, depending on how you count the edges, right? So still about 500 times the number of people on Twitter edges, which is basically scales. There's some constant 500. Maybe it's maybe it's closer to 20. Then it's 20 times the number of people on Twitter. It still basically grows linearly with the size of the users. But then there's someone like Obama who has basically a constant fraction of Twitter is following his account, right? So if you want to create a bot on Twitter and you want it to look like, try and make it not seem like not make it seem like a real person seem like a real person on Twitter, you're not going to follow just 500 random people. You're going to pick like Obama and like like Justin Bieber, I think might be the number 2 person, most followers on Twitter with over 100 million. And I think like Katy Perry is up there. You're going to follow these people on Twitter and then maybe some random people on top of that, right? So you want the graphs look more like this, and they have these kind of structural patterns as well. So how do we find so both these so there are kind of 2 questions that are important to ask. How do we find these communities, and how do we find important nodes and edges in the graph? Okay, so the important edges kind of so the important edges can be kind of it's sometimes dual to the important nodes. You can just reverse the roles of the nodes and edges. You're kind of connected to another. Think of an edge as connected to another edge. If there's a node that links both of them, you can kind of reverse these roles. And finding communities, we've already seen one way how to do this, which was spectral clustering. Okay, we'll see another one, a couple more that we'll focus on in this lecture. A difference is spectral clustering. This forced a partition of the graph. I need to put every node in exactly one of the communities. So it can't be in 2 communities at the same time. And even these nodes that aren't really connected to anything, I need to push them into a community. I differ in the notion of clusters and communities as so a community is going to be a tightly connected so a subgraph. Okay, so I'm going to define as V as a subset of all the vertices V prime and all edges kind of which are defined by V prime. So between 2 nodes in V prime, I count those edges. That's like a subgraph, and that would be a kind of a tightly connected one with lots of edges in it would be a kind of strong community. So this is what we'd be looking for. And some of spectral clusters would find this for us, but it would, because it has to partition, it doesn't quite satisfy this. Now, this will be a good starting point, but we'll see some other ways to try and find this. And important nodes and edges, we saw, so PageRank was one way of doing this for important nodes. As I mentioned, there's this kind of dual way of thinking about it. You can find important edges through PageRank as well. How often, I can either just run PageRank and then multiply the stationary distribution Q star times the probability I move to that edge, and that gives me a PageRank score for the edges. I can also do this dual representation where I connect edges together and run PageRank again. We're going to see a different way of finding these important nodes and edges as well. And it turns out there's a way to sometimes convert from these to finding these communities. So let me start with this notion of kind of betweenness. Okay, so there are a variety of ways of defining kind of this defines. This is one of the most classic ways of defining important important edges in a graph. Okay, and I can so I can then say remove these important edges, and then the remaining connected components would be would be like the communities. Okay, so an example, let's say I have this graph. Okay, and so if I deemed that this edge was important and say this edge was important, and I remove them, then for instance, this community would be left connected, and this community would also be left connected. And these would be two communities, and maybe this point by itself. That point is uninteresting because it's just by itself, but the other ones might be important communities once I've removed these red edges. Okay. Okay, so this betweenness, okay, is defined. So the so I want to find the betweenness between edges A and B. So the betweenness between vertices A and B. The betweenness would be the fraction of all the shortest paths that use edge A, B. Okay, so if I look in this graph here, okay, and I look at the shortest path between, let's call this edge C, and this is E over here. The shortest path between C and E, well, it goes up here, and I have to basically use A to B, the edge AB to get between C and E. Okay, so this is one of the shortest path edges. I look at all pairs of vertices, and I calculate the shortest path between them, the smallest number of hops, and if it uses edge AB, that increments its betweenness, and then I divide by n choose 2. Okay, so I have to basically, so the computation of this is a bit painful. I basically have to do something like computing all pairs shortest paths. And then there's some issues when there are multiple shortest paths. I need to kind of distribute the weight I get for each shortest path onto the edges. I get to, you know, this shortest path increments these 3 edges, not just those 2. So the total between this is not some of all the edges is not a fixed number. But there are a variety of things I have to do to calculate this, and this is kind of hard to calculate at large scale, but this is a good notion of how important is an edge. This edge I've highlighted here, this red one between A and B, actually would be deemed fairly important in the graph because anything from the left side that wants to have a shortest path to the right side has to go through this edge. So think of this as like if there's a highway system and there's a big river like the Mississippi River, and if there's a bridge that goes across from Mississippi River, that's going to be a really important bridge. Or if there's we're in Salt Lake City, so we're mountainous, if there's a road that goes through the mountains between 2 communities, that road is going to be very important because there's not a lot of ways to go back and forth. Whereas if I'm in like downtown, there are lots of streets in between places. Those roads themselves are not too important. So what it says is, okay, if this is, so if I'm thinking like this group over here is downtown, SLC, and this group is like Park City. There are only a couple ways to get between downtown and Park City, but once they get up there, there's lots of connections in between there. So this edge, which might be this might be like I-80, you know, up like Parley's Canyon, you know, that's a pretty important edge connecting those. If that road goes down, then I can't get in between them. If there's a network, an internet network, and you know, to send stuff on the internet between the U.S. and Europe, or U.S. and Asia, there are actually these cables that go under the ocean. That's hard to believe that this is how it works sometimes, but there are these massive cables that go under the ocean, and those cables are pretty important in the internet connection. If those get cut, it's a big deal. So those are high betweenness edges. So I want to route something. It approximately finds the shortest path based on some measure of not just distance, but the busyness, which is estimated online. And edges which get used a lot have high betweenness. Those are really important edges. Okay. So this is kind of an important notion, and then I can find communities by cutting these edges. Say I cut the edge between Parley's, you know, Parley's Canyon is closed. You can still maybe get on some back roads if it's not the winter, you know, and those roads aren't closed. There's even without the winter, there's other ways to make it up there. But let's say I closed all these because of snow, then I have these different communities. Okay, and so this is one way of showing it, how to find this using graphs. But this can be generalized to things that you can't draw pictures of as well. And so I can give every edge between the scores, and I can gradually kind of increase the cutoff of, you know, it has to be above a certain level. When I get it, I get smaller and smaller communities which are left isolated by not having these large edges. In a friend group, someone who connects two different social groups would also have a high betweenness score, perhaps. Okay, these would be important relationships and stuff like that. Okay, so let's get back to another notion of communities, and this is probably the most popular notion of community called. So it's this notion called modularity. And modularity is a score. So it's not an algorithm. The algorithm will discuss how you would find this, and that isn't necessarily easy again. A lot of these techniques were defined by sociologists, by people in like actually physics. There's a subclass of physics which studies behavior of networks, and modularity came out of a group of people in physics. You know, the notions are great in that from modeling they work well, but they were not thought of with computation in mind necessarily. Okay, so this is defined. I've got some graph with vertexes and edges, and I want to have a score, the modularity score, often use Q for historical regions, on QC, where C is going to be a subset of the vertices. Okay, and QC is basically going to be the fraction of edges in the subgraph induced by C, right? So in this community, minus the fraction or let's say the expected fraction of edges in the subgraph induced by C, right? So again, just so it's clear, if I have this whole graph here and identify 3 nodes as being in C, then the subgraph are going to be these edges here. It's not going to include these edges, even though they have one vertex in C. I want to include these don't count as being being inside the groove. Okay, this is a little bit different than the notion used for clusters and spectral clustering. Okay. Okay, so I want to somewhat measure the fractions that are in there versus the expected fraction. Okay, so the fraction which are in the group, right? So this part here. So I can think of defining all this by starting with the adjacency matrix. A, right? And this is basically Aij equals 1 if edge Ij is going to be in the edge set, otherwise is 0, right? So this is the 0, 1 matrix that captures these edge relationships, and so then the fraction inside this notion here would be the sum over Ij, which is in the cluster, and I add up this terms Ij, and I would divide this by the total number of edges, right? So that's the fractions inside. Okay, so in this so in this example here, I'm going to have 1, 2, 3 edges, which are going to be inside, right? Out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. The size of the, let's see, the total number of edges is going to be 9. So this would be 3/9 here in this example. Okay. Okay, but the more interesting thing is the expected number of edges. So for the expected, I'm going to define another matrix, which so I'm going to write 1 over E, the sum Ij in C times Eij. Okay, I guess I've overloaded uppercase E here, but I'm going to define the expected number of edges. Edges Eij is going to be equal to the degree of j times the degree of I divided by 2 times the total number of edges. Okay, where Dij is the degree of Vi. And so, for instance, in this case, if this was Vi, the degree is now 1, 2, 3, 4. So the degree of I is going to be equal to 4 here. So this is the number of edges which touch this vertex. Okay, and we have to divide by 2. The reason we're dividing by 2 is because every edge is touching 2 vertices, right? So the sum of all the degrees is going to be kind of twice this number of edges. Okay, so what we're saying, and the important concept here is the expected number of edges is going to be proportional to the size of the degree. Just by having a high degree is not necessarily going to be an important subcluster. You want it to be tightly knit community, not just people who have these high degrees. Okay, so you want to say, okay, if one of my nodes in a cluster has a high degree, well, I expect them to have a large number of edges. right? So an edge between di and dj is proportion to the product of the 2 degrees. So if I have 2 high degree nodes, I kind of expect them to follow each other. I expect Obama and Bieber to kind of follow each other because they're both very, very popular. It's more likely that there's an edge between Obama and Bieber than there is between me and a random person on Twitter, right? So so it's right. So it's kind of, that's what the core thing that this modularity is capturing is it's not allowing these communities to be just these nodes with the really high degree. Otherwise, things just based on density, like think of density-based clustering, this has its limitations because just these dense areas are not, could be a dense cluster, but it doesn't necessarily mean there's a tightly knit community. There's just that there's happens to be a lot of stuff going on here. This is saying there's some background distribution which is uneven on the distribution of these degrees because we're not in this Erdős-Rényi model of graphs. So the degree distribution is different. But if I find a community that's tightly connected, so I have a lot of edges, even if I have high degrees, or if I don't have high degrees, but I still have a lot of edges, then that's it. Then that community is going to be more tightly knit. The modularity score is going to be high. Okay, so let's go through a small example of this. Okay, so let's say the modularity score, let me write this up here, is now going to be turns 1 over, you want to normalize this by 4 at this point because there's a double sum here, but the modularity score is going to be over all vertices in a cluster, the kind of count those number of vertices divided by the expected number of vertices in this cluster. Okay, and so now let's draw some graph. And this is something that's kind of hard to see in pretty small graphs here. I need to have a pretty tight cluster to get a high score, but let's say that this graph is almost complete. Let's say this is C here. Okay, so this is my guess of C, but there are these other edges as well that are going on in this graph, and maybe I have this one guy who's very highly connected down here. So this person's degree is actually pretty high here. Okay, so let's write the degree of each of these things. So this guy is the degree of 3. This is degree of 2, of 3, of 3. This is 1, 2, 3, 4, 5, 6. Degree of 6, 2, 1, 2, 3, 4, 5, 6. 6 again. 2, 2, and 2. Okay, so these are the degrees on the graph. Okay, and now let's work out the modularity score. Let's count just the number of edges inside the graph. Actually, let me add, I feel this might not be big enough. Let me add one more of these edges here. Okay, so let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. So the sum of ij and c of aij minus, well, let's just say this part is going to be 8, and the sum, so there are 8 edges inside this cluster. Now let's figure out what the expected number of edges is. Okay, so this is a little bit tricky. This is going to be, let's see, the total number of edges in the graph is going to be 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, great, great. So nice round number there. Okay, so this edge is going to get a score of ij here is going to be 3 times 3 divided by 2 times 17. Okay. And this 2 times 17 is going to be the same everywhere, this bottom part. So let me just write down the product of the two things everywhere here, and we'll add those up. So this is going to be 9. This is a 9. This is a 6. This is a 12. This is an 18, a 9, an 18, and an 18. Okay, so the sum of all these guys is going to be 18 to the 72 plus 81, 87, 99. Okay, so the total ij eij, if I did this correct, is going to be 99 over 34. Okay, so I got, and then this number here, which is just some normalizing coefficient, this enforces that Q of C is going to be, I think, in -1/2 to 1. There's some rationale behind that, but so this total value here in this graph is going to be 4 times 17, which is going to be 34, 68. Okay, so the total modularity is going to be 8 minus 99 over 34. This is about 3, right? So I expected, let's say I'm expecting about 3 edges in this graph, in the subgraph C, but I got 8, which is great. That's big. The bigger, the better, the more of a subgroup. So I'm going to have, this will be divided by 68. So this is roughly about 5 divided by 68. And that's going to be, was about 1 over, 1 over 14, something like that, right? Was that too big? Yeah, so roughly this is the modularity score, and the larger this is, the more you say, the more of a community this is going to be. Okay, and so this score is nice in that I can then, if my goal is just to find the communities, so then I want to do is to find the communities C, which are a subset of V, with the largest modularity score, right? So with the largest score here, right? These are going to be my communities, and I didn't have to set any parameters here, right? So with other forms of clustering, I had to set some parameters. K-means clustering needed the value K, right? Spectral clustering, I have to keep dividing the graph until I stop at some point. Right here, I don't have to set any parameters. One thing I can do is I can run spectral clustering, and I can keep subdividing. And at every subdivision I do, I can compute this modularity score. So that would be one way to search for it. You can also try optimization techniques. Like I could say, well, let me consider adding this node in here. Right? It has 2 edges, so I can add it in there. Does that increase or does that decrease the modularity score? The problem with searching is that it's a very kind of discrete optimization. So it's not like continuous optimization. I can't run real full gradient descent on this. So this becomes harder to do. What people would do instead is they would probably do the right thing to do. I wrote a paper a long time ago that said you could run a discrete optimization like this variance, but it got stuck in local minimum all the time. The right thing to do is probably like some random walk. I could define a Markov chain where I start with the cluster and I decide to add or delete these vertices. And if the modularity scores goes up, I'm more likely to accept that change. If it goes down, I accept it with some probability. right? This metropolis algorithm sort of way of doing a random walk. And over those, I keep track of the largest scores I've seen. That's probably be how I'd recommend doing it. In the notes, it has this idea of trying to add everything that increases the score individually at once and trying to do this. And you can seed that with spectral clustering, the best spectral clustering, and then I do some local optimization. Right, so this is kind of how this kind of modularity process works. And then there are various algorithms of how to try and calculate it. But there is kind of secretly a parameter in here that some people have started to talk about, that I could put some parameter in here, some gamma parameter at this point right here, that basically says how much do I weight having a large number of nodes. If this is gamma is small, I weight the A part larger. And if I want a small expected number of nodes, well, then I weight the gamma larger. And so there is this kind of parameter you could put into here, although most people don't do this. So it's kind of parameter free, but it doesn't really come easily with an algorithm the way spectral clustering did or PageRank did. They were naturally built around these algorithms. So, okay, I should say one more kind of important concept. If you haven't heard about this in graphs before, there's this notion of these cliques in graphs. Okay, and so a clique is a set of vertices. Again, so let's say C subset of V, where all edges ij in the subset have an edge ij in C, in the edge, in the set of edges, right? So if I have a graph here, okay, the only cliques here are the boring things. All vertices themselves are cliques, right? Each individual vertex is a clique. Every edge is a clique, is a two clique. If I do this, then this counts as a, this is a three clique. I can also, this is a three clique, but I can also add in these edges, and now this is a four clique. Okay, so these edges, this is a kind of a very restrictive form of finding these communities. I say, if they really are a community, everyone must be friends with each other, right? And so can I find these cliques? Can I find the largest clique in a graph? Basically, there's this NP-hard problem, or which is the, given a graph, is the largest clique bigger than some value k? Determining that is NP-hard. That's a very hard problem. As long as k can be very big. The thing is, most cliques are actually pretty small. So it turns out they're not that hard to find in practice. You can use something like, actually, in practice, finding cliques is not too bad. It's basically the a priori algorithm. Basically, I kind of start with all edges, and then I find all kind of triples of edges, which have this kind of the same three vertices. So I find all, so this is basically, this is the two cliques. This is the three cliques. So I basically enumerate, I start with an edge, right? So I'm going to start with an edge here, and then I'm going to look at the two vertices, and if this has an edge, then I check this third one to see if it forms the complete picture. So for every edge, I pick a vertex and I enumerate all of its other edges, and I check to see if this thing then goes back to this other thing. And that's why I find all the 3 cliques. And then I do a similar thing, use to the 4 cliques. I basically start with all the 3 cliques, right? So now if I were to do this here, I would say start with this 3 clique, which I've already found. And now I'm going to say, I'm going to check, right, I'm going to check this edge here. Say, okay, this is one of the vertices in this 3 clique. I'm going to check this edge. Oh, okay, now this vertex, does it have an edge here and an edge here? If it does, I found a 4 clique. I can do the same thing with this edge as well, but this one does not a 4 clique. So then I stop the search, right? So think of, I'm doing this breadth first search down all possible 4 cliques, but I can do a lot of pruning. So for here, I want to use kind of 3 cliques and expand kind of greedily. Okay, and I keep trying to expand them. And the thing is, in most graphs, the number of these, the largest number of elements actually peaks around the 3 clique. Sometimes there are more edges than there are 3 cliques. In very structured graphs, there are more 3 cliques than there are edges, but there usually are not more 5 cliques than there are 4 cliques. That's pretty rare. So this process actually gets faster and faster as I get to larger and larger cliques. And so it peaks when I'm finding 3 or 4 cliques. Once I get past that, I can keep finding larger and larger cliques. Okay, and then these would also be a good starting point for modularity or for one of these other kind of local expansion techniques for finding clusters. I can maybe add things on which are almost cliques and do that search in this combinatorial way as well. Okay, so this was a discussion on community. This is the last lecture of the semester. I will I'll post the final end term on Canvas on Sunday evening, and then I will send out information about the poster session. Probably soon. We'll probably get some more detailed instructions out by the end of the week. So I'll hope to see you all at your posters, and then we'll so I can't see you in person, but feel free to stay in touch. If you're still going to be around the university after this semester, hopefully we'll actually get to see each other. So okay, so that's me logging off for the semester. I'll be around for office hours.